So this is part 2 of moisture, clouds, and precipitation. But before I get started, let me just tell you all how much I miss you. I love teaching about weather, and I'd much rather see your faces in front of me while I'm doing it, but it is what it is, so let's get started. In this slide, you'll see that relative humidity is increasing because we're adding water vapor to the flasks while keeping the temperature the same. It just makes sense that if we keep the temperature the same, in this case at 25 degrees Celsius, then if we add water vapor, the relative humidity is going to increase. If we remove water vapor, then the relative humidity is going to decrease. This next slide shows what happens to the relative humidity when temperature changes. As the temperature cools, the capacity of the flask to hold water vapor goes down also. We start out with 7 grams at 20 degrees Celsius, and the relative humidity is 50% because the flask is holding half of what it could. Then if we cool it to 10 degrees Celsius, we see that the saturation mixing ratio is 7 grams. The vapor content is 7 grams. So the relative humidity is going to be 100%. The relative humidity is increased by decreasing the temperature. Then we get over to the third flask that's been cooled to 0 degrees Celsius. The water vapor content is now 3.5 grams. What happened to the other 3.5 grams? Well, look at the capacity. By the way, saturation mixing ratio is the same thing as capacity. So if you look at the capacity, it has decreased to 3.5 grams. What happened? The flask was holding 7 grams of water vapor. So what happened to the other 3.5 grams? Look at the flask. You see liquid. So condensation has taken place. Because the air could only hold 3.5 grams at the cooler temperature, the other 3.5 grams condensed out of the air. This is basically what happens in the real world when you get clouds or rain. The air reaches saturation by cooling. Later on, we'll look at the mechanisms that can cause this to occur. Pay attention to the graph. The lowest temperature usually in the early morning. So what happens when we have those low temperatures? The relative humidity increases. Warmest temperature of the day usually in the late afternoon, so look what happens. When the temperature goes up, the relative humidity goes down. So the picture of the glass there, we see what's happening to it, that we have a dew or condensation that's forming on the outside of the glass. Why is that happening? Because the temperature of the air has cooled by direct contact with the cold glass to the dew point temperature. Water vapor in the air has condensed because of this. This slide shows the inverse relationship between relative humidity and temperature. As the temperature goes down, relative humidity goes up. As the temperature goes up, relative humidity goes down. And remember why this is happening. It's because the capacity of the air is changing as the temperature changes. As the temperature goes down, the capacity of the air to hold water vapor goes down. As the temperature goes up, the capacity of the air to hold water vapor goes up. So we get this inverse relationship between the two. This slide shows again the relationship between temperature and the saturation mixing ratio. Again, don't forget, saturation mixing ratio is capacity. So at 104 degrees Fahrenheit, look at how much water the air could hold. It's 47 grams per kilogram. Compare that to minus 40 degrees Fahrenheit. 0.1, a tenth of a gram is all that the air is able to hold, and it's at its capacity when that happens. Now you're beginning to understand just how important water vapor is to weather processes. So it's very important to know how much water vapor is in the air. In other words, what is the humidity of the air? The instrument that we use for measuring humidity is called the hygrometer, an electronic gadget for measuring the amount of moisture in the air. There are different types of hygrometers, like a sling psychrometer. It's a type of hygrometer consisting of 2 thermometers mounted side by side. One of them has a little cotton wick attached to the bottom of it. So we measure 2 temperatures. The dry bulb thermometer, the one without the wick, measures the air temperature. This gives us what we call the dry bulb temperature. Then the cotton sock is wetted and the psychrometer is spun for about 2 minutes. The spinning provides the energy for evaporation to take place. Evaporation is a cooling process, so energy is being taken from the air to evaporate the water, and as that happens, the air temperature will cool because we're removing energy from the air. This means the temperature on the wet bulb thermometer will decrease. The greater the difference between the air temperature and the wet bulb temperature, the drier the air is. Low relative humidity. If the difference between the two is small, the higher the relative humidity. The air is close to saturation, so very little of the water on the wick can be evaporated. Now, if we were in the classroom at this point, I would be doing a demonstration with a sling psychrometer so that you could actually see that this is what's going to happen. But the best I can do is show you the next slide and give you a link to a YouTube video showing how a sling psychrometer works. What you're looking at in this slide is a sling psychrometer. 2 thermometers mounted side by side on a swivel. One of them has a little cotton sock or wick attached to the end of it. This measures the wet bulb temperature, and the other one does not. With that one, we take the air temperature called the dry bulb temperature. Since we can't do this in the classroom, I've enclosed a link to a YouTube link, for you to view to see how a sling psychrometer works. The dew point temperature then is the temperature to which air has to be cooled to reach saturation. So whenever we see a cloud that's forming in the sky, we know that the dew point temperature has been reached. A good way to determine what the relative humidity is. Compare the air temperature to the dew point temperature. If they are close together, the air is close to saturation. Summer in Sacramento, we might have air temperature of 102 degrees and a dew point temperature of 30 degrees. What could you surmise about the relative humidity, high or low? Recall the recipe for a cloud, or in other words, the recipe for condensation to occur. Water vapor, condensation nuclei, and cooling temperatures. Let's look at a real-world example of cooling and condensation. One of the ways that air can cool is to be forced up a mountain. This cooling is called adiabatic cooling, which is a fancy term that means air rises. As air rises, it cools by expansion, and as it descends, it warms by compression. These are adiabatic temperature changes. The air starts out unsaturated at a temperature of 30 degrees C. How do I know it's unsaturated at 0 meters and 30 degrees Celsius? Because the diagram shows no clouds. But as it rises, it cools at what we call the dry adiabatic rate. Dry because the air is unsaturated. This rate is 10 degrees C for every 1,000 meters. At 1,000 meters, look what happened. A cloud is formed. That means the air is now saturated. 100% relative humidity has been reached. 1,000 meters is the lifting condensation level, and 20 degrees Celsius is the dew point temperature. And this is the exciting part. Look what happens to the rate of cooling from 1,000 meters to 3,000 meters. It's less, and you should know why. Condensation has taken place, and the latent heat locked up in the water vapor has been released. As long as the air inside the cloud remains warmer than the air outside the cloud, and it has a good chance of doing so because of the latent heat of condensation, keeping it warmer, it will continue to rise, but will cool at a lower rate that we call the wet or the moist adiabatic lapse rate. We're going to assume for the purpose of this diagram that all the moisture gets squeezed out on the windward side of the mountain. So as the air descends on the leeward side of the mountain, it will warm back up at the dry adiabatic rate, 10 degrees C for every 1,000 meters it descends. This is why the leeward sides of mountains are drier than the windward sides. They are said to be in a rain shadow. Think of the snowy conditions on the windward side of the Sierra Nevada mountains and how much drier conditions are on the other side. It's actually a desert there. We call these orographic effects. Oros is a Greek term for mountains. So that's it for part 2. Stay tuned for part 3.